If we can switch off these lights, it might be look better. Okay, so let's continue where we left off. Yeah, so just before lunch, we had inverted this already, right? Did we? Yeah. So we had inverted this already, and we saw that we can now get the angular velocity in the body fixed frame of reference, or rather the angular accelerations in terms of the angular velocities. And we saw that a strange feature of rotational motion, that even when there is no torque that is applied to the rigid body, you could still have the change in angular velocity because there will be a non-zero angular acceleration. So this is something that will exist even in the principal axis when we get to the moment of inertia along the principal axis and set all of these off-diagonal terms to 0 by getting to B1, B2, B3 special choice wherein these off-diagonal terms would go to 0, you would still have the possibility of the angular accelerations being present even in the absence of some of external torques acting on the system. So that's something that you need to be kind of aware of and not be surprised by, especially when you encounter such a situation in some of the problems. You already have your next homework posted, so some of them might hinge upon this. Yeah. So now that we have introduced this concept of the inertia matrix, so far we've been working on inertia as if it was a scalar, and we are familiar with this term inertia from Newton's first law as something that kind of resists the acceleration, or rather increase in motion. So that's something that we have kind of generalized now to three-dimensional status, and we've also looked at the possibility of coupling that can happen when your choice of B1, B2, B3 is general, right? So let's get on, and we'll use the same color coding. That green is something that we have already looked at, and the red or yellow is something that we are moving towards based on concepts that we already know. So inertia is a concept that we already know, but the generalization to 3D and more so in a matrix form is something that we introduced today, and we'll try to learn a few more features of that. So now, as always, we try to simplify our work and see if there can be situations where we can get rid of some of these terms, or rather make a more complex general expression simpler for certain cases, and that is symmetry. Typically, most bodies that we will deal with have planes of symmetry. For example, since you're in aerospace engineering, aircraft have typically a plane of symmetry which is involving the x-axis and the z-axis, which is about which you have the roll and the yaw. So roll, yaw and sideway drift is typically coupled but decoupled from the rest, which is essentially your forward motion, your vertical motion and the pitching motion, okay, which also of course changes your angle of attack. So similarly, if you look at, unless you have strap-on boosters, etc., you can think of rocket engines as having two planes of symmetry, or rather even axisymmetry, okay. So that kind of again can simplify your inertia matrix, so you don't need to live with the full 3x3 matrix that we talked about or introduced just before lunch, okay. So we will take look at some of those things. In particular, what does symmetry do to the products of inertia, which is what I have abbreviated as POIs. So we will see how the POIs get affected by such symmetries. Okay. Now, all of those equations that we derived were for torques which are applied about the center of mass, and also the angular momentum that was resulting was about the center of mass. And though we converted those Euler's second law to Euler's dynamic equations more in terms of angular velocities rather than angular momenta, still we are left with the choice that we started off that derivation with, namely the point about which this is done is the center of mass, because it's about that, and of course inertially fixed points, that this simplicity of the rate of change of angular momentum being equal to the applied torques occurs, and therefore it's important to keep that initial assumption in mind for all of the derivations which follow from that. Okay. So the product of inertia about the center of mass is equal to 0 for any rigid body or its part if certain forms of symmetry are there. So one case is either or both the axes representing the product of inertia. Remember that the product of inertia were the product of either x and y, or y and z, or z and x, essentially integrated over dm over the entire body. And that can go to 0 if one of those, let's say we are talking of IXY, that involves x and y as a product in the integrand of that definition, right? So if either one of that is x or y, are axes which represent the product of inertia, that is, if in the case of IXY it's either x-axis or y-axis, if those two axes happen to form the plane of symmetry, like in the case of the aircraft, as I said, it's the x-axis towards the nose of the aircraft, and also the z-axis which is going downwards. This is a plane of symmetry. So IXZ, for example, has to go to 0. But any I which is having one of these will also go to 0, is what this essentially says. So one plane of symmetry means that there are two products of inertia which will go to 0, and that's the case with the aircraft, because it has just one plane of symmetry. On the other hand, a rocket has at least two planes of symmetry. Even with strap-on boosters, many a times you can see that there are two planes of symmetry, and when that happens, all the three products of inertia will go to 0. In other words, all the off-diagonal terms of our inertia matrix vanish, and it becomes a diagonal matrix, and that makes rocket dynamics from that perspective simpler compared to aircraft dynamics. Okay, so now again, there's something that we have already learned and something that we are trying to do over here. So what we already know, and in fact you showcased in some of your homework problems as well already, that the parallel axis theorem works, right? Now we are trying to generalize that and see how it works with, let's say, the products of inertia, for example, is end result we would like to get to by the end of the slide, is to say that if you have the product of inertia about any arbitrary point P, and you already know the product of inertia about C, this is also something that you will see a lot of appendices in textbooks will typically give you that. So using that, you could find moments of inertia about any other point in your homeworks, but now can we do something similar with the products of inertia? Yes, we can. So there we had the distance squared between the two axes which were parallel and passing through those points of interest. Here it will be a product of the corresponding coordinate measures, because we are talking of a product of inertia associated with the x and the y axis. So therefore you would have xp and yp. Xp and yp are of course the coordinate measures along those same b1, b2, b3 system. Now in this case specifically about b1 and b2, and the origin, remember, there was at the center of mass. So this is essentially a position vector from the center of mass projected onto the x-axis and projected onto the y-axis, and essentially that product is what you are multiplying the total mass of the rigid body by and subtracting, because remember, in the very definition of the products of inertia you have a negative sign, and that's why here negative sign here, whereas in the parallel axis theorem for moments of inertia, you will remember that we have a positive d squared times m that is getting added up, which also said that in that case you had the, let's say, the minimum moments of inertia about the center of mass, and the same directions if you go to any other point about which you want to determine the moment of inertia, it would be larger because of that plus md squared term. Whereas here you need not, because the signs of x and y also matter. Sometimes it can be larger than that about c, sometimes it can be smaller than that about c. In other words, the second term can either be overall positive or overall negative. So be prepared for that, that IISc is neither the maximum nor the minimum. It can lie anywhere in between, and choice of point P makes the difference, right? So let's get to this result. So are moments of inertia about 2 points related? Yes, of course, we know that, in fact, we have utilized that. For example, we said that the moment of inertia about the z-axis, about point P, is related to the same about point which is at the center of mass. And that's what is the result that we already had, that the moment of inertia about any arbitrary point P is the moment of inertia, same moment of inertia. If it's zz, this is also zz, about the center of mass, and then you add the mass times mass of the rigid body times the distance between C and P about the same axis, that is the z-axis passing through C, the z-axis passing through P. You essentially measured that distance, and that's essentially your d squared over there, right? Which is also, in other words, x squared plus y squared, and which is why x squared plus y squared is the definition of the moment of inertia IZZ as an integral of x squared plus y squared times dm, right? Now, since we're talking of point P now, essentially it's the x and y coordinates of P. The Pythagoras theorem comes in handy over there. So where xp, yp, zp, of course, are the coordinates of P with respect to C. In other words, we have first of all introduced these unit vector system b1, b2, b3 fixed to the body, rigid body, which is undergoing translation and or rotation. In particular, we are now focusing on rotation, and we need to also fix the origin for that coordinate system, and that we are fixing at the center of mass. And from that, we are saying that we can deal with equations about any other arbitrary point, whether that point P is like a point Q which is part of the body or not, doesn't matter, okay? Whether it is fixed inertially or not, doesn't matter. So any arbitrary point, this will work, and this is a very useful relationship. So essentially generalizing that moment of inertia relationship using the parallel axis theorem, we can also prove that the products of inertia follow a very, very similar rule. So this is the relation between products of inertia about any 2 points. One point is, of course, a point of choice, the center of mass. The other is an arbitrary point, and this is a xy products of inertia related. The same thing you can generalize to the yz and zx directions as well. Yeah. So now we'll continue to extend the use of the parallel axis theorem, the way you have been deploying it for various homework problems. We will try to see how you are using the moments of inertia with parallel axis theorem, how you can now use with the products of inertia. So one such thing is in terms of if you could decompose complex shaped rigid body into some standard shapes that are part and parcel of that overall shape of the rigid body, then you can work from the parts upwards towards the overall rigid body by having a summation, and for each one of them you might have to invoke the result that we had at the end of the previous slide, so that we can then move it from the center of masses of those individual parts. Could be a sphere, it could be a cylinder, it could be let's say a thin plate, rectangular plate, for example, or a rod, etc. From that to the overall CG or the center of mass of the rigid body as a whole. So that you can do by using this second term over here and then summing over all the parts that compose that particular larger complex shaped body. So it's commonly used to find the moments of inertia that you already know. Now you can see that it can be used for finding the products of inertia as well about the center of mass for a single rigid body which is composed of multiple parts. And if the mass and the moment of inertia or the product of inertia of each part about its own center of mass are known, because that is essential. So here you see that this is about the center of mass Ci of the ith part, and of course you should know the location of the center of mass itself, Ci, which is where from you can get this xci, yci, etc. So that then you will be able to get to the I of the entire body about C for the z-axis. So this is something that you have been already using. Now we are just generalizing that to this product of inertia, just replacing your x squared plus y squared by an xy product of the same quantities, and with the appropriate sign, which is what we introduced when we defined the product of inertia as opposed to the moments of inertia. Okay. Now, though we typically deal with inertia as a matrix, and that is sufficient for this level of course, like AE2220, it's important to remind ourselves that inertia is actually a tensor. It's a second rank tensor, so what we call as a dyadic. And when we use it in that form, there's no need of a basis. Just like for a vector, the unit vector system is required to get its measure numbers for that particular system. But a vector exists by itself irrespective of whether you have already chosen a set of bases to represent it or not. It has a certain magnitude, it has a certain direction. Similarly, a dyadic is associated with two sets of directions. For example, the stress tensor is also a second order dyadic like this, and that's typically associated with the plane on which the stress acts and the direction in which the force on that plane acts. So those two contribute to the two different sets of directions. Similarly, your inertia is also kind of a dyadic, and the right way of representing I omega, which is what we've been referring to as the torque, the sum of the torques is equal to I omega. The I would actually be a dyadic. So in the typical representation of that, you know that scalar quantities, for example, pressure, you don't use any underline, whereas in the case of a vector quantity like velocity, you put a single underline. In the case of a stress or a strain, we put a double underline to indicate that two directions are essentially associated with it. The same is the case with what we have introduced now, the inertia dyadic as well. It's a second order tensor, and in that sense, the right way of mathematically rigorous way of writing that particular equation, where we've been writing the torque, for example, would be to write I dotted with omega. Okay, so this is the right way of putting this, and this dot product essentially contracts one of these indices between I and omega and gets you to a single index, which is what is on the left hand side as well as a vector. But in the actual implementation of that for numerical calculations, etc., I becomes a matrix and omega becomes a column matrix. Similarly, your M also becomes a column matrix when they are expressed as measure numbers or along a particular set of chosen bases. Whereas this particular equation is valid irrespective of which basis you choose. It's a more fundamental, mathematically rigorous equation that you need to be aware of. So without going into the nitty-gritties of tensor analysis beyond the scope of this course, we'll just introduce a few concepts in terms of going towards the principal moments of inertia, because that is essentially an eigenvalue problem that you're solving for the matrix I, and the eigenvalues are what constitute the principal moments of inertia, and the eigenvectors correspondingly will be the directions of the principal axis. So similarly, I don't know, you probably haven't taken the deformable bodies course, right? So when you do that, you will see that similarly for the stress as well as the strain, you will be doing a similar eigenvalue problem to get to the principal directions of stress, the principal directions of strain, etc. So once you learn this from a mathematical perspective of how to do for this, all of those will become just a change of variables. You're just using another variable in place, but the mathematical jugglery that is involved or the procedure that is involved is one and the same, right? So if you're looking at the moment of inertia about any arbitrary axis, even before we get on to principal axis, then you can get I and n by just dotting this I on either side with an n. You will end up with your I and n. So remember that I and n is a scalar quantity. So if you are looking at I and n, you can always get it by the dyadic I. You're pre-dotting and post-dotting with the vector n. Okay, so this has two indices. So in other words, you have IXY, IXX, right? So it has two subscripts that go with it. Now each one of these dot products are going to remove those, and essentially you're getting into a particular value of I, which is essentially a scalar quantity, which is the moment of inertia about the n-axis. The n could be x, n could take on the value of y, n could take on the value of I hat, j hat, and k hat. So when it takes on those specific values, you can very easily see that all that we are doing is to get to the diagonal terms of the matrix. So irrespective of which system you have chosen, B1, B2, B3 could be any arbitrary orthogonal system that you have chosen to get to I in the first place. But once you have there, you can get the normals also expressed in the same basis, B1, B2, B3, in which you have expressed I. Then you have n transpose I n. So it's the same thing what I have written here as a tensor equation. The matrix version of that is over here, and that's how you actually execute a calculation eventually when you want to get to numerics. So where n is the unit vector along the desired axis. So so that's as far as moment of inertia is concerned. It's quite clear. So just a direct extension of that to products of inertia is that you had in the previous expression, the first equation of this slide, both sides you had n. Now you're just going to have one side, you're going to have m, and other side n. Two sets of unit vectors are required. Two axes are required for the product of inertia. For example, IXY involves x and y, which means B1 and B2. So you'll have those on either side, and you will end up with that. So it's very easy to see, for example, if you're taking m and n as one of the B system itself, you're just going to extract out the corresponding off-diagonal term over there. For example, if I take m as B1, then this m transpose is just going to be 1, 0, 0. And if I take this as B2, then it's going to be 0, 1, 0. Okay, so when you do that, you see that it's going to pick you the second row first column, and that's essentially your 2, 1 term. And because this is a symmetric matrix, it doesn't matter whether it's integration of xy dm or yx dm. Because of the commutative nature of multiplication of scalars, you end up with the same thing, and in either case you will end up with either imn or inm, with the second and first row or the first and second row. But the utility of this is that you can use m and n as any arbitrary set of unit vectors. They need not be b1, b2, b3. Okay, so that's the utility of this particular expression that you can use to determine this in any other direction that you would like to determine. For example, in this morning's homeworks also, many of you are working on multiple frames which were rotating with respect to each other, right? So you have unit vectors associated with each one of those frames, and sometimes you might know the inertia matrix with respect to a certain frame, but you want to determine it with respect to another frame. You can very well use these two sets of equations to populate your inertia matrix about the new sets of axes, new set of orthogonal dextral triad that you have. You can go ahead and populate that, right? So the importance of this, of course, this is valid only when these are orthonormal vectors. In other words, they are orthogonal to each other, mutually orthogonal, perpendicular to each other, and they are normal as well in the sense that they are all unit vectors.
So,
yeah.
M and N are orthogonal to each other?
That's correct, yeah. So when they take on the same value, it becomes a moment of inertia. When they are different from each other, they have to be perpendicular, and they end up in a product of inertia. You might recollect in the beginning, I also introduced the concept of non-orthogonal coordinate systems. Also, we talked about curvilinear coordinate systems, etc. There is a concept of inertia associated with those as well, but it follows the same thing, but needs a little bit more generalization. But not that this concept does not exist for such cases, but in this course we are limiting to orthogonal systems and which are rectilinear in nature. So therefore, we're not taking into account curvilinear or non-orthogonal systems. Yeah. Finally, the inertia matrix in, yeah.
So if you knew, this kind of goes back a little bit, if you knew like the moment of inertia in the NM coordinate system, and you wanted it in, say, like an IJ
Yeah.
you would write N and M in terms of IJ.
So, yeah, what you would do is you would write IJK in terms of N's and M's.
Yeah.
And then you would populate those column matrices as the measure numbers, and you can get it. Yeah. So the inverse works. Yeah. So the inertia matrix in two different frames. Yeah. So this is actually something that you kind of directly asked. So I have this last equation is something like that. So remember in the previous class we introduced the concept of the direction cosine matrix. So the 3 by 3 matrix which can convert from one system to another. For example, if you have a direction cosine matrix T which converts between the B1 and the B2 system, then you will have the moment of inertia directly found out using this. So one is to use the measure numbers of the unit vectors along the directions in which you want the moments and products of inertia in terms of those in which you already know the moments and products of inertia. The other way is if you know the direction cosine matrix between them, you just pre-multiply by it and also post-multiply by its transpose, and you will end up with converting from the B1 system to the B2 system as far as the inertia matrix is concerned. Also remember that the I's are about the same point. So if this is about the center of mass, that's also about the center of mass. Okay. Next, we want to look at using that set of equations that we introduced, which were for arbitrary N and M, for a specific special choice of N and M, so that you can end up getting all products of inertia 0, and you are left with only the diagonal terms. This is called as the principal moment of inertia about C. And it's valid for a certain set of directions which are mutually orthogonal to each other, and we need to determine that. And between these, in fact, you can also find that out of these three principal moments of inertia, one of them will be the maximum principal moment of inertia, and the other will be the minimum, and always everything else will exist within that as far as the moments of inertia about the center of mass are concerned. So this also helps you indirectly to get to the maxima and minima as well, which is many a times important, because if you want to reduce the impact of a torque on a body, you would apply it about the axis which has maximum moment of inertia, so that you would have the least change in your angular velocities, and vice versa. If you want a large effect of it, you would apply it about the minimum moment of inertia axis, so that you can implement a larger change in the angular velocities, right? So now we want to relate the principal moment of inertia and the principal axis with whatever we already know. Now the idea is in trying to get to this, the question that we ask ourselves is, can we choose a set of axes with 0 products of inertia even without a plane of symmetry? We already know that special cases when you add planes of symmetry, like in the case of the aircraft, the XZ plane, or in the case of the rocket, any XY or XZ plane, we know that those are planes of symmetry, and therefore the associated products of inertia will go to 0. So you will be left with either all of them going to 0 or at least 2 of them going to 0, and we're left with only one product of inertia in the case of the aircraft. Okay? So if that is the case, even when there are no planes of symmetry, can you still do this, that you can get rid of all the off-diagonal terms, or in other words, get them to 0 values? Yes, it is possible, and that is if you can set up this problem. Remember, from that general equation that we had, all that we are saying is that if the multiplying factor for n is either a matrix or a scalar quantity, the result should be the same. In other words, what that matrix multiplication of the vector is doing is just scaling up or scaling down the magnitude of the vector, but it is not affecting the direction of the vector, which is what eigenvalue problems are all about. So eigenvalue problems can of course be stated in many standard forms, but one form of stating it is that an eigenvalue is one which is a magnifying factor for a vector without changing its direction. The matrix for which those eigenvalues are, pre-multiplication by that matrix also does the same thing as the scalar multiplication. So that is the beauty of this particular specific choice of n and the corresponding IPs which go with it, which are the principal moments of inertia. The principal moments of inertia in this case will become your eigenvalues, and the n's will become your eigenvectors, which are the principal directions of inertia. And remember, many people get confused because this principal direction is used in so many different subjects that the principal directions for inertia is very different from principal direction for stress or principal direction for strain, etc. The procedure, the eigenvalue problem is exactly the same, but the actual meaning of physically what it is very, very different. And for example, in a stressed body, you can have at different points different principal directions for stress, at different points different principal directions for strain. But for a given rigid body, you have only one set of principal directions and one set of principal the principal moments of inertia, which are the eigenvalues. Okay, so about the center of mass. About other points, of course, again you could have different, but at a given about a given point, you have only one set each. Okay, so when multiplied by any orthogonal unit vector, this above equation should result in 0 products of inertia. So that's essentially what we are saying, that because you remember the previous slide, we talked about pre-multiplying and post-multiplying by n and m, and then getting to this. So now all that we are saying is that irrespective of what orthogonal unit vector, it has to be orthogonal to n, but any in that plane you can choose. So if this is n, in the plane which is perpendicular to it, you can choose any one unit vector, and whichever unit vector you take, if you pre-multiply this equation by that, you would end up with 0 products of inertia. So that is the beauty of this particular choice of n. Okay, so this leads to the eigenvalue problem with 3 eigenvalues, and those 3 eigenvalues are what you see in the end result here as well, the IP1 to IP3, which are the principal moments of inertia, and the corresponding principal directions of inertia are your eigenvectors n1, n2, and n3, about which the principal moments of inertia exist, but the products of inertia vanish. Okay, so use 3 principal axes as the rigid body axis. Remember that we were talking of the B1, B2, B3 system. That was an arbitrary choice. The only constraint on the B1, B2, B3 was that it should be fixed to B. It should be having an origin at the center of mass, and it should be fixed to B. As B rotates, the B1, B2, B3 system should rotate with it. But it could be any direction. Once 2 are chosen, of course the third gets determined, but the first 2 can be quite arbitrary, of course mutually perpendicular to each other. But now we are talking of a specific choice of B1, B2, B3, which can make our life simple in terms of a lot of calculations, because these off-diagonal terms vanish, that is the products of inertia vanish. So in mathematical parlance, we say that the matrix has been diagonalized. We had a fully populated 3 by 3 matrix. Now we have diagonalized that matrix, that so that only the principal diagonal elements are in general non-zero, the others are all zeros. Okay. Now, we'll go back to a special form of Euler's second law, which we studied in the morning's class, where we called it as the Euler's dynamic equations, when we expressed everything in terms of angular velocity instead of angular momentum, right? So now if we take that and now we go about special choice of B1, B2, B3 as N1, N2, N3, which are essentially your principal directions, then you can see that the equations, the Euler's dynamic equations simplify quite a bit. But still you see that the second term, which was the cause of concern because it was the source of nonlinearity, a quadratic nonlinearity in the omegas, that continues to remain. Okay, the first term is no problem. It's just saying that this is what you would see as a natural extension of Newton's laws to Euler's laws, or even Euler's first law to Euler's second law, that you have an external torque and its components, or measure numbers rather. Those are directly related to the corresponding moments of inertia about the principal axis, about the center of mass, multiplied by the angular accelerations about the three directions, alpha x, alpha y, alpha z, right? But in addition to that, we have seen in morning's derivation that there is this quadratic term in the omegas, and that is that can exist in general even in the, as we see now, even when you have gone to the principal directions, unless IZZ is equal to IYY, then the first equation simplifies. Similarly, if all three are equal to each other, that is the principal diagonal terms in the moment in the inertia matrix, that is all the principal moments of inertia are all equal to each other, for example a sphere or a cube for example, in such cases all these three will vanish and you would have a very, very simple set of equations to deal with, almost a direct analogy with the translational motion your rotational motion will become, right? But now of course it's not the case. We start with the general case where we had it in the general B1, B2, B3 system, where all of the products of inertia exist in general. In other words, they're all non-zero. Then we are applying the special case where we are taking the products of inertia equal to zero, because that is the choice of BIs that we have made, right? When we do that, all of these off-diagonal terms vanish, and the equations that you have at the bottom is what we end up with. Any questions on this so far? Yeah. So now that we have looked at one form of Euler's second law, which is in terms of angular momentum, again there we looked at about the center of mass, about an inertially fixed point, about an arbitrary point. Then we moved on to what were a special case of Euler's second law, the Euler's dynamic equations, where we replace the angular momentums in terms of the angular velocities. Then within that we went to an even more special case where we chose the B system, B1, B2, B3 as the principal directions of inertia, and therefore ended up with the simplest form that we can get to of the Euler's dynamic equations. But there are a few other forms which sometimes are more useful for solving certain problems. So we'll try to take a look at that now. So now, because almost all of EDEs that we talked about, the Euler's dynamic equations, were about the center of mass. Now we know that there is another special point, or set of points rather, which are inertially fixed points, and about them, which can typically be, let's say, a pivot point of a body, which is kind of hanging at a nail point, or it could be an axis about which it is rotating, which is common between the body and the inertial frame, so frame of reference. Then you would have also the simple form of Euler's second law valid, that the external torques resultant will be equal to the time rate, or inertial time rate of change of the angular momenta about the same point. So if that is the case, let's see how EDEs change that is the form of the Euler's second law, but in terms of angular velocity, how does that change when we get to the point, inertially fixed point, rather than the center of mass? Okay. So remember that the generic notation we had used for that point is O, to refer to any inertially fixed point, and we said that just like M and H about C, M and H about O are also related by this simple equation, that if you sum all the external torques about O, you end up with the inertial time rate of the angular momentum about the same point, that is the inertially fixed point. Then we are, of course, working mostly in the body fixed frame. So we would like to convert this d by dt from the inertial frame to the body frame, which means that I have to have the bd by dt of the same term along with an omega cross. As we know, with all vectors this works, and this works here as well. So the angular velocity, of course, of interest is the inertial angular velocity of the same body B, whose angular momentum we are involved with, right? So that has to cross the angular momentum about the inertially fixed point O. So when we do that, it's very easy to see. If we just have to substitute the values for HO and omega BI in the B system, and then we end up with this particular equation. And many cases in the practical implementation of this, you might have to, of course, use the parallel axis theorem whenever the IXX, IYY, and IZZ need to be determined. You will add a MD squared term, and when the off-diagonal terms need to be determined, you will add a M times XO, YO kind of a term, where XO and YO are essentially the coordinates from the point of interest to the point inertially fixed point, and therefore you can get to those as well. So once again, of course, as expected, you would see a term which is kind of analogous to translational motion, which involves just the inertia matrix times the angular accelerations, but the other one is involving an omega squared kind of behavior, and therefore the quadratic nonlinearity once again creeps up as anticipated. Okay. Now, many a times it's quite easy for us to introduce certain intermediate frames, like what you did in today's examples as well. For example, the angular velocity of one body with respect to another was very, very complicated. You introduced intermediate frames to have simple angular velocities, and then you added them up to get to the angular velocity of one body with respect to other, which has a fairly complex motion. So similarly, for a lot of axisymmetric problems, including some examples from today's homework, which you solved in the morning, you will see that even in terms of employing the Euler's dynamic equations, these intermediate frames of reference are going to be of great utility. So what we want to end up with at the end of this slide is this particular equation, which says that the torque about the center of mass in any arbitrary frame G, which could be an intermediate frame, neither the body frame nor the inertial frame, but somewhere in between, is given by these terms, and you can see that it has a very, very similar form to what we have been looking at already, that it has one term which is kind of analogous to translational motion, which involves the corresponding inertia matrix, but now expressed in G, and d by dt of the angular velocity, which is nothing but your angular acceleration, but once again with respect to that intermediate frame G rather than the inertial frame, which is what we were talking about earlier. And then, of course, this second term, which involves this G over here instead of I. So, but the interesting thing is that whereas the Newton's second law is valid only for inertial frames of reference, your G need not be an inertial frame of reference, and still this particular equation is valid, because it's kind of an intermediate relating relationship, and in that sense it is still valid, but because many of the quantities that we are taking here, for example the angular velocities, are all inertial angular velocities. So Even though the overall expression is taken in the G frame, note that what you're having inside is an angular velocity of B in I. Here again you have an angular velocity of B in I and angular velocity of G in I, and which is in some sense taking into account the fact that Newton's second law and therefore all of Euler's equations, first, second law, as well as the dynamic equation are all valid only in inertial frames of reference, but still we can always utilize that result to work with certain intermediate frames which may or may not be inertial frames of reference. So now, of course, the simplicity that we have in this case is axisymmetric problems that we would like to focus on in this slide. For axisymmetric problems, we can consider an intermediate frame of reference G in which the moment of inertia is the same as in the rigid body for B. Because if you have an axisymmetric problem, it's always possible to choose another set of axes about which you have the same moments of inertia as from the original set B1, B2, B3 that you had. So because it's an axisymmetric problem. So for example, you have this as an axisymmetric body. So now if I choose my B1 along this and B2 and B3 in a cross section, now if I rotate this by a certain angle, I know because this is an axisymmetric body, my principal moments of inertia, or for that matter the moments of inertia about this B1, B2, B3 system will not change, right? So that's essentially what we are talking about over here, that for axisymmetric bodies it's always possible for us to find frame G. In fact, there are many such frames. You could find a frame G in which the moments of inertia are the same as in the frame B, the original frame that you started off with. Now the key is that in the intermediate frame of reference, the rigid body rotates only about the axisymmetric axis. So in other words, this rotation, as I was showing you in this example, was to go from one frame to another, I'm taking a rotation about the axis of symmetry, which is why it works, that the moments of inertia are the same in about both these sets of axes. Okay, so now we can write the Euler's dynamic equations in either the B frame or the G frame of reference, and we are using the same coefficient matrix, which is I, which will work with both. Right? To reduce the confusion, of course, since both are valid, we can choose one of them and continue with that. So rewrite the equation in the B frame of reference with the detailed notation. So this is how it looks. Now you compare this to what we are getting towards. You're just replacing B with respect to G in most of the representations, but not in terms of the angular velocity itself, etc., which is anyway going to be the same, okay? Because if they are going to be different from each other just by a constant rotation, then it really doesn't matter whether I write omega B of I or omega G of I. So that's essentially what we are talking about here, right? So now just to write in an equation form what we already stated, that the moments of inertia are the same about both of these axes. You're just saying that the moment of inertia I about C is the same whether it's in the G or the B frames, and that's a constant, right? Therefore, your Euler dynamic equations in this special choice of intermediate G, we are saying special because these are equal to each other, okay? In that sense, it's special. But within that plane, as I said, which is perpendicular to the axis of symmetry, you can choose any G. All of them will be special indeed. Okay, so now similar to the equation in the rigid body frame of reference that we already had, that is the B system, except for differentiating the angular momentum now in the intermediate frame of reference G. So this is additional tool we will have whenever we are dealing with axisymmetric problems. Many a times it might be more useful or simpler to deal with another frame G, which is shifted from the original frame B by just an angle theta about the axis of rotation, and then we can employ the same set of equations. Once again, of course, the sum of the torques about the center of mass is going to be the inertial rate of change of the angular momentum about the same center of mass, and therefore can be broken up into two parts, which is the change. Now instead of earlier we were writing B here, now we are just putting it as G, the time rate, and of course your angular velocity is also of g in I, which is one same as your b in I if it's a constant rotation between the two. Okay, because what we're talking of is the rate of change, not the actual value, right, of the rotation. So now the intermediate frame of reference and a fixed point. Well, remember we've been talking about this inertially fixed point, O. So which had certain simplicities, just like the center of mass. Sometimes more convenient to use O instead of C, which is what we are talking about here. Now, along with the intermediate frame of reference concept that we introduced in the previous slide, it's just an extension of the intermediate frames that we already introduced to calculate angular velocities of more complex systems, just extending that to the inertia and the Euler's dynamic equations. So we can write the Euler's dynamic equations for the rigid body about an inertially fixed point O, and in terms of the measure numbers in special intermediate frame of reference. We know that whether it's the center of mass or the inertially fixed point, we know that the time rate of inertial time rate of change of the angular momentum is going to be equal to the torques applied, of course, about the same point, whether it's center of mass or the inertially fixed point. So now it's the special case that we are talking about where the moments of inertia did not change. So that special case is frame G instead of B that we are taking up. So, as I said, the reason why I call it special is because the moment of inertia remained unchanged when we moved from B to G. So when you do that, we end up with this equation that we already saw. Okay. So I think with this we complete, and also we have sufficient I think the syllabus, the content, whatever we started off to cover, we have covered. Initially, I had plans of taking into account the impulse momentum equations and also the energy equations. When I talked to some of my colleagues at Georgia Tech, they said that they typically don't cover this in this particular course. It's done in more advanced courses, though I think it's simple enough concept to actually be covered here. But anyway, since that is what is generally done at Georgia Tech, I will skip that. Of course, I introduced basic aspects of that in the second class itself when we talked about integrating with respect to time, integrating with respect to displacement, etc. Integrating with respect to time gave us impulse, integrating with respect to distance gave us energy. So we were able to correlate work with change in kinetic energy. We were able to correlate impulse with change in the momentum, translational momentum. Say there are similar concepts in rotational motion as well. Not so straightforward because of some of these complications that arise, but essentially the procedure is very similar. So with that, we will see if we can cover a very short review of whatever we have done in this whole course, not going through every bit of detail, but how much ever we can do. And then anyway, as usual, I'm going to share this slide deck with you so you can go through those summary slides, and we'll be done. We'll of course have next Monday's class because you're going to present your homeworks, but most probably this would be my last lecture. Okay, so let's look at where you came from in terms of the prerequisite for this course. It was statics, and then we moved on to dynamics and the various extensions. Essentially, you're going from Newton's first law to Newton's second law. That is the right-hand side of this equation, which was 0 earlier. That is, you were just summing up forces and moments and setting them to 0 for static equilibrium. Whether you write it in a rectilinear form as the measure numbers along particular directions, or if motion is only along a particular direction, then you have these scalar equations. Otherwise, you have vector equations. That's something that you are already familiar with even in statics. All that we did when we moved on to dynamics is took that right-hand side, which was 0, and said that no, it is the time rate of change of your translational momentum, okay, which translational momentum represented by L, and we took the dot of that, and truly speaking, this is what it is valid in, and this is valid, and of course this is a vector, but here, when you're talking of rectilinear motion, you can talk of scalars, or even if it is a general 3D motion, you can break it up into measure numbers along the 3 orthogonal directions, and each one of those becomes scalar equations, and you can deal with in this particular way. So already this particular going from this to this itself, already one assumption is there that this time rate has to be in an inertial frame, okay, because it's a vector. Though we are writing right now as a scalar equation, its components or measure numbers of that vector, and therefore how you take that dot is important. And the second approximation came in over here. We assume that masses are constant, so we could take that out of the derivative term and just take dv by dt in an inertial frame and call that as the acceleration, right? So now that was for a particle. Now that particle could be a part of a system of particles. It could be also a part of a rigid body, etc., which is the generalizations we did when we went to the Euler's equations. And going from the scalar equations to the vector equations, quite straightforward. We were just trying to take everything into account over there. The final thing is, of course, the equation of motion for orientation in 2D. Okay, so the rotation is about a fixed axis or general 3D rotation, and when you do that, you end up with the equations which are very similar to the equations on the top, but now in terms of rotational quantities, which is the torques and the angular momentum, right? And also in terms of the approximations, one and the same. Once again, you're talking of inertial frames, and you're talking of I constant, not changing, and therefore now you can write it as I times d omega by dt, which we call as alpha in a scalar sense and in a vector sense. But in a vector sense, we saw that the change in omega, because omega, the way the angular velocity is mentioned, not always can you write it as I times alpha, okay? So that's something that you will be get to see in some of your homework problems as well, and you will see why this is kind of different from what you talked about here. So translational accelerations are much simpler to deal with. Angular accelerations are much more complicated animal to deal with. Okay. So then we went on to look at further the particle dynamics. So I think I pretty much mentioned this. So the first part is about inertial assumption. The second is about the constant mass assumption. Then, of course, we talked about the time derivatives of both the position vector r as well as the velocity v, taken once again in the inertial frame of reference. So strictly speaking, I should be putting a pre-superscript of I on both of these to indicate that's what is happening over there. Okay. Now, in terms of one jump that we took from statics to dynamics is that statics required a certain level of understanding, which involved measure numbers and vector addition, vector measure numbers as well as vector addition. But then in this course, we are primarily the new addition was vector differentiation, and we said that the frame of reference choice about which the differentiation is done is important, and we were able to correlate differentiation in different frames using the angular velocity of one frame with respect to the other as well. Now, as far as Cartesian frames of reference are concerned, as long as they're inertial, you would have quite simple results, kind of quite easy extension from statics. But once you get into non-Cartesian frames of reference, we saw quite interesting things. We'll look at that. And then in terms of going from the description of motion to the causation of motion, we introduced the concept of forces, and then we saw how those can affect the translational momentum, and similarly in the case of rotation, how the torques can affect the angular momentum, right? Now, if you apply Newton's second law to each particle in a system of particles, so in other words, we are extending from a single particle to a system of particles, which in a special case can also be a rigid body. So in that case, you are applying to each particle that it is composed of, and then you are summing it up, right? So, so you see that the summation of the forces is equal to the summation of the inertial time rate of change of the translational momentum for each individual particle, and then you're essentially summing it over all the particles that the system is made out of, and then we invoked, remember this is a very important point, many people tend to, once they have used it, they tend to forget about it, that Newton's third law was built into this, that the internal reaction between two particles belonging to the system were kind of cancelling each other out, the interaction forces. Otherwise, this could have been fairly complicated. So it's Newton's third law in many problems, not only in dynamics, but in many other courses, you will see that it's one of the most fundamental laws, and it's used many a times almost as if it's taken for granted without giving appropriate credit to it, because without that, most mathematical models will be extremely complicated. Now, so this is what we ended up with in terms of the second derivative of the position vector. Once again, of course, inertial derivatives. Assuming the inertial frame of reference and constant particle masses, so interchanging the order of summation and differentiation, once again, this is what happens. You can see that first you have the d squared by dt squared summation, and then you take, you had the summation first, and now you're taking the d squared by dt squared out of that. So this is the d squared by dt squared that was there over there. And then if the mass is constant, which is the case with most problems that we typically deal with, or even if there's a small change which happens because of fuel burn, etc., it's kind of a negligible contribution compared to the large accelerations that the aircraft can have, for example, and therefore this happens. But in the case of the rocket engine, that's not the case, because the propellant weight fractions are very large, and also there's a discrete change when the previous stage is shunted out, and therefore the mass can change discretely, and all of that needs to be accounted into this. So certain subtleties like that need to be remembered, though most of the problems we've been solving are with constant mass or constant inertia, right? Now, the first law, Euler's first law, is an extension of Newton's second law to the translation of rigid bodies. We were just talking about, instead of talking of all particles of the rigid body, we just focus on one point in the rigid body, may or may not even be an actual material point. For example, a hollow sphere will have it at center where there is no material. That center of mass's acceleration is what we are following, and we are saying that the sum of the forces which act on the rigid body is equal to mass times the acceleration of the center of mass. Then once again, in terms of the same thing expressed in terms of the time rate of change of the translational momentum, which is in fact the more appropriate thing. It's actually from this that we go to that one in the case of constant mass. Next, continuous rigid bodies and integrations over areas and volumes. So we saw that many a times these integrations need not actually be done, because these are for standard shapes and they already exist, and even when you have complex shapes, it can be broken up into standard shapes, and also you have the parallel axis theorem, etc., so you can kind of utilize them. So one is in terms of, first of all, defining the center of mass. How do you locate this was the equation. So you just get the center of mass as 1 by mass times the summation of the locations of each individual mass elements, or if you think of it as set of particles, each particle, right, its position vector. And in fact, it was this equation that we used to even simplify one of the equations that we had today in terms of an integral of to an arbitrary point q from the center of mass, RCQ, times dm. So integral of RCQ dm equal to 0. So that's essentially coming from the rigid body version of the system of particles version. So system of particles has a summation, it's discrete, whereas here you have an integration, it's kind of continuous, and that's what you end up with in terms of calculating the mass as an integral of the mass density times the volume element, and you have the once again the location of the center of mass, once again something that you don't normally need to do for most problems, because these are available as standardized tables, and along with that, of course, you'll use some other conversion factors. So yeah, so it's the same thing. Yeah. Then we talk about the kinematics. I'm shuttling between kinetics and kinematics, though we covered all of kinematics first and then got on to kinetics. I'm kind of in this review mixing up the two to showcase the correlation between one slide and the other. So now we're talking of kinematics of particles and the rigid body's center of mass, the inertial Cartesian frame of reference. You have RC, the position vector, you have VC, the velocity vector, and AC, the acceleration vector, all of them expressed in the I hat, J hat, K hat system, and the corresponding measure numbers are essentially going into dots and double dots because your I hats, J hats, and K hats don't change with time. So if that is the luxury you have, that you have defined everything in terms of the inertial frames coordinate system and the unit vectors which are fixed to the inertial frame, then this is what you end up with, right? So that's an inertial Cartesian frame of reference. So nothing special. It's just like working in rectilinear motion, just that the effort involved is 3 times the effort because you have to do the same thing for the x direction, y direction, and the z direction. So that's all that is there, but the process is the same. Now, because the inertial frame of reference unit vectors are unchanged in the inertial frames of reference, which is the reason why you don't worry about the dots of I, J, and K. You're only worried about the dots X, Y, and Z. Okay, so then we went on to one level of complication where we introduced the polar coordinates and then generalized it to 3D to cylindrical coordinates. And there we saw that, yes, the directions of the unit vectors were changing from point to point, and therefore we needed to take time derivatives of those as well, not only of the measure numbers. So we started off the position of the center of mass, which we said that just go distance r along the radial unit vector and distance z along the axis of the cylinder in the cylindrical coordinate system. If it was just a 2D problem, then this zk hat is not there and just that term is there. So already there's a huge simplification in the position vector. Instead of 3 terms, you just have 1 term. But just that the other things, once you take the time derivatives, become more complicated, right? So the new thing that you see is in terms of ER changing when you go from point to point, and that change is encompassed in this in terms of an R E theta, and that's why this second term comes. Even though the position vector did not have an E theta term, the velocity does have an E theta term. And the complication becomes even more once you go take the second derivative, because all of this is because of the chain rule. You're taking the derivative of product uv, it becomes u dv plus v du, and therefore each time you have a 1 term, instead it becomes a 2 term, and that's why the number of terms goes on increasing, right? And here we encountered something very special, that first derivatives with respect to time can also contribute to acceleration. Our always intuition is that only second derivatives contribute to acceleration, but we saw that first derivatives do contribute to acceleration. There were 2 such terms. One we refer to as the centripetal acceleration that you see here on the negative radial direction, and then you have the Coriolis acceleration, which is along the theta, E theta direction, and it's positive. Okay, so you can see that there are no second derivatives in either of these terms. That is the speciality about this. So certain takeaways: unit vectors change direction with the position, which is why terms like this crop up. Okay, now then so do the unit vectors as well, because position vectors changes direction. Unit vectors are also changing. Unit vector derivatives are always perpendicular to itself. This is an important point which is of great utility, and in fact we utilized it in a lot of derivations as well, because it's by definition a unit vector. Obviously it remains a unit vector in the sense that its magnitude is always 1. So its magnitude cannot change, then obviously there can be no change along the direction of the vector itself. That if at all it has to change, it has to change in a plane which is perpendicular to that. And for example, if ER hat has to change, it has to change along E theta hat, and similarly if E theta hat has to change, it has to be along ER hat, and that's already kind of included in these derivations, right? The third important interesting takeaway is that the velocity and acceleration are nonlinear functions of the non-Cartesian coordinates. For example, you see that r and theta are both variables, position variables. Now they are not appearing just as a linear term like in the first term over here. It's appearing as a cubic term. It involves one r and two thetas. So it's actually appearing as a cubic term over here. It's appearing as a quadratic term over here as well. So you see these kinds of nonlinearities crop up when you're dealing with non-Cartesian coordinates, but you still use them because for certain problems it becomes for certain problems it becomes much simpler, and that's why you end up using them. Now, also we talked about the first derivative contributions of centripetal and Coriolis, right? Another complication other than non-Cartesian was to go for rotating frames. The non-Cartesian could still be an inertial frame of reference. What we are talking about here could still be inertial frames of reference. Now we are talking of a frame which is rotating, and therefore it's also accelerating, right? Any rotating frame, the directions change, and therefore accelerations are occurring, and therefore it's no longer an inertial frame of reference. So it's non-inertial frame of reference. Unit vectors are changing with respect to time, and that's where the angular velocity concept arose and became very useful indeed for calculating a lot of things, especially time derivatives. Okay. Next, we look at the RB's orientation, again in kinematics. Now, we're still dealing with kinematics, but we are now talking about rotational kinematics of the rigid body. Things that we talked about started with the simplest case where we had simple rotation. That means rotation is about only one axis all the time within the duration of interest, and that fixed axis, about that fixed axis, that direction of the axis itself became the direction of the angular velocity vector, and the magnitude of that time rate of change of that rotation became your angular velocity magnitude. So you just needed one angle to define that. That angle is the rotation about that axis of rotation, of course. For example, if we call that as theta, then with respect to the reference orientation, which is the inertial frame of reference, then you have just a scalar rotation. So in the 2D problem, we saw that as far as the translations are concerned, vector equations were necessary. But as far as rotation was concerned, just a scalar equation was sufficient because there's only one scalar variable associated with rotation, namely theta, and that theta, its time derivative became omega, again its time derivative became alpha. That cannot be done in a general case. That has to be remembered. This only for that 2D kind of rotation, simple kind of a rotation, right? So one may rotate multiple times also. We saw that in many of your example problems as well. Let's say if it's a two set of rotation, first by theta 1 and then by theta 2, then you could see that the final rotation was theta 1 plus theta 2 because the rotation was about the same axis, and the additive addition is of course commutative as well. In other words, you can undertake rotation 2 first and then 1 instead of 1 first and then 2. So theta 1 plus theta 2 equal to theta 2 plus theta 1. Then, whereas when we went on to, for example, the direction cosine matrix, etc., remember that the 3, 2, 1 was different from 3, 1, 2, etc. The sequence mattered, okay? Whereas here in simple rotation, it does not matter, okay? So it's simple rotation, typical in any 2D analysis, and it's far easier to handle compared to 3D rotation because a lot of these commutative nature, the additive nature, etc., make the calculations fairly simple. But once you get into 3D motion and it's no longer infinitesimal rotations, if it's infinitesimal rotations, even 3D is very easy to deal with. But once you get to what is known as finite rotation in 3D, then it's no longer a vector, first of all, that angle. We saw how complex it was. One way of handling that was using the direction cosine matrices, but that's not the only way. We will list out a few other ways. In fact, we talked about the Euler's way already. There are a few other ways as well. I'll just mention them in passing as well. Now, it's not a vector in the R3 space. By R3, of course, we mean the real numbers in a three-dimensional space. And for some of the finite rotation representations, we have to go to an R4 space, what are known as quaternions, etc. Okay. Now, yeah, I think I'll mention that here, quaternions. Yeah. Quaternions are another way of expressing the rotation. We have learnt in this course only two ways, mainly, that is the orientation angles and the direction cosine matrix. When I introduced the orientation angles and before I went to the direction cosine matrix, I also mentioned the Euler parameter, in the sense that Euler said that irrespective of how complicated a rotation from one position to another position from time t1 to t2 might be, you can always, apart from the translations, you can always get the rotation done through a single axis of rotation and a single rotation about that, which is what gave us the unit vector about that, and also the magnitude of the rotation, and therefore we were talking about 4 quantities associated with that. There are various versions of that, and typically most of them, when they involve 4 parameters instead of 3, they are called as quaternions. And there are certain advantages and disadvantages in terms of singularities, avoiding singularities, etc. Another very common method which is used especially in structural analysis of beams and plates is the Rodriguez parameter. The Rodriguez parameter also involves only 3 variables, just like the orientation angles, like what we did, the yaw, pitch, roll kind of 3-2-1 sequence, something similar to that, but much more interesting. It avoids certain singularities and things like that. We have not looked at that. There are others, such parameters named after other researchers as well. Now, compared to all of them, the number of parameters involved in the method that we stuck to, and the results of which in fact you used in today's homework, just certain terms you took from the direction cosine matrix to solve certain problems, but there are essentially 9 terms there. So in other words, you're dealing with more number of terms, but you avoid a lot of issues like singularities, etc. So in that sense, you're dealing with what looks a little more messy, but avoids a lot of issues in the derivations, quite straightforward to use, which is why a lot of people prefer and continue to use the direction cosine matrix. And for large finite rotations, it's a go-to method for a lot of problems like aircraft dynamics, etc. Okay. Then the most complete and processible way to represent 3D rotation, therefore that method that we introduced here, it's always introduced in a first course in dynamics, like what we did. 9 parameters, but you might say that if only 3 angles are required, why 9? So, but you know that all of those 9 depend on that phi, theta, and xi, right? Cosines and sines of that. So essentially, there are only 3 independent quantities on which the entire matrix depends. You might have 9 different values, but they're all functions of 3 sets. Another way of looking at it is that you have 9 parameters, but there are 6 constraints, because you know that this is an orthonormal matrix, the direction cosine matrix. So the transpose is the inverse, and if you multiply C transpose times C, you get the identity matrix, and that's of course symmetric, C transpose C by definition. So you would see that there are 6 equations associated with that, corresponding to the 3 diagonal terms, all of which are equal to 1 on the right hand side, and 3 off diagonal terms, 3 independent off diagonal terms, which are all equal to 0. So therefore you have 6 equations. So in other words, you have 9 parameters in the because it's a 3 by 3 matrix, but you have 6 constraints, 3 off diagonal and 3 diagonal constraints, and therefore 9 minus 6, only 3 independent quantities exist over there, right? You can change the orientation multiple times, say by C1 and C2. This is similar to what we were talking of in the simple rotation case. We were saying that the simple rotation by theta 1, theta 2, you can add them up. Here, you are not going to be able to add them up. You are going to multiply them, okay? But still, the simplicity remains, because just like addition is commutative, multiplication is also commutative. Sorry, multiplication is not commutative, but you can essentially break that up, because there's a matrix multiplication that we are talking about. So they're not commutative. So you have to be careful, which is why that 3-to-1 sequence was important. So you had to go in that particular order, right? So the final orientation is multiplicative, and the finite rotation, 3D rotation that you have is of course non-linear. You saw cosines and sines of the angles that are involved. Obviously, if you are going to express that in Taylor series, for example, you will have infinite series for that. So it's essentially a quite non-linear in form because we are dealing, remember, with not infinitesimal quantities anymore, that we can approximate sine thetas by theta and cos thetas by 1. So you have all highly nonlinear terms, and as I said already, these are non-commutative. Next, let's continue about rotational kinematics, and we introduce, apart from angular velocity, the concept of angular acceleration as well. And in the once again starting with 2D problems where you had just an axis of rotation and therefore simple rotations about a fixed axis. Without loss of generality, we can take that axis to be the z-axis, and therefore the k hat is the unit vector about that. Then you see that there's only one angle of rotation that you need to deal with. It can be a scalar problem if you're dealing only with a rotation problem. That angle is theta, and its derivative, time derivative in an inertial frame is omega, but once again, because it's a scalar quantity, that would not matter because that axis of rotation itself is fixed in an inertial frame of reference. And in a vector form, of course, it takes this form. And then for any vector, arbitrary vector p, which is fixed in a rotating frame of reference, you can take the time derivative of that by just taking the cross product, pre-cross product rather, with the angular velocity, and then you end up that. So that's the, so apart from the fact that angular velocities describe motion, rotational motion, a very important utility of the concept of angular velocity is in terms of avoiding to take time derivatives many a times. You can just take a cross product to get to the time derivative if you have the expression already for the angular velocity. Okay. For any vector, say, let's say the velocity, for example, you can go from time derivatives in one frame to the other just by adding a term which is the cross product of the angular velocity with that same vector, and that's something that you know even in your dreams now because you've used it so many times, right? Now, when we get on to more and more complex systems, we'll have more and more frames of reference, more and more intermediate frames of reference, etc., which is why I have been stressing many a times at the point of even being boring to use the precise notations, because it may seem like redundant for many problems that you did, but if you cultivate that as a habit, you will see that it's very, very useful in tackling many real life problems, and also kind of writing algorithms and computational codes based on that, or even using AI systems, etc. In many cases, it will become very useful if you are quite particular about the notations that you use and don't make for convenience kind of notations, right? Now, angular velocity is additive. So direction cosine matrix was multiplicative, but the angular velocity is additive. In fact, you use this in a series again, even in today's problems, so you're kind of aware of that. But angular acceleration is not additive. So yes, it has those same two terms as the angular velocity did, but it has an additional term as well, okay? And that additional term is a cross product between two angular velocities, okay? So this is something that you have to be aware of when you introduce especially intermediate frames of reference, or you already have frames of reference or rigid bodies in the problem definition itself, which involve a rotation between two adjacent rigid bodies going on in a sequence. Then you might have to use this in a series, and there you should not forget this third term, because this is unique to alpha, it is not present in omega. Okay, then we talked about two interesting theorems. One is about 2 points fixed on a rigid body. The other is about a single point which is moving on a rigid body. And when you had such points, there were easy ways of determining that. In fact, in many of your problems at the top, you would say formula 1 point, formula 2 point, etc. So essentially, to utilize that 1 point formula or 2 point formula, as these are typically called in the literature. And so if you look at, even before we get to that, the angular acceleration, of course, is I d by dt of omega bi. So it's all a question of taking in the right frame the derivative, also expressing the vector whose derivative is taken in appropriate form, so that you know whether the unit vectors are changing or not. If they are changing, you should make sure that their derivatives are accounted for as well. in the chain rule, right? So then you have this utility that, in fact, without even mentioning, many of you actually utilize this in today's homework problems, that you are interchangeably taking these derivatives, sometimes in B frame, sometimes in I frame, which was correct, because for this particular vector it doesn't matter, okay, because the other term is going to be the cross product of angular velocity with angular velocity, that is anyway going to go to 0. So that's why you see that these two are equal to each other irrespective of which frame you take it in. So as long as it is between angular velocity of one frame with respect to the other, those two frames you can interchangeably take the derivative with respect to, okay, valid only for angular velocity vector. Now for the 2-point problem, you just have any two arbitrary points, doesn't matter what those points are, they might be on the body, in the body, off the body, doesn't matter, but as long as they are associated with the body and move along with the body, in other words, they are fixed with respect to the frame of reference, also fixed to the rigid body, then you can relate the velocities, which is again just a direct extension of what is valid for any arbitrary vector. We are applying it for just the position vector. When we do that, we get the velocity of one point, again all inertial frames. So the velocity of one point with respect to the velocity of another point, the difference is only in terms of a cross product of the angular velocity with the position vector between those 2 points. The order is very important. Sometimes when you're talking of angular momenta, you have a reverse thing, so just be careful when you're applying that. Here it is going from the point whose velocity you know to the point whose velocity you do not know, whereas when you're talking of angular momenta, etc., you're essentially dealing with the either the torque or the angular momenta about a particular point, and therefore it is from that point, and therefore you would see the reverse form of this. So just be careful, because that can change the sign of this particular term and can lead to errors in the overall answer, right? So the same thing when extended to the acceleration, of course, makes it a little more complex. Once again, you have a translational acceleration contribution, a rotational acceleration contribution, and also a centripetal acceleration contribution. So this plus, as we saw, because of the nature of this cross, will become negative anyway, so that's why it's a centripetal acceleration, the second term, middle term over there, right? So that's the first theorem, 2 points fixed on the rigid body. Second is about single point, which is moving on the rigid body. All that you do is, at the instant in which you are interested, you mark the point on the rigid body, which is fixed to the rigid body, where that moving point was, and then you start tackling the velocity of that. So then it becomes quite easy to get to the velocities of that moving particle. The moving particle is called P. We want the velocity of that P in an inertial frame. All that you do is take the velocity of that point on the rigid body, which was instantaneously coinciding with the moving point. We call that O prime. We take that velocity again in the inertial frame. Then we add to that the velocity of P in B, because we know how P is moving in B. Example was that stone problem that the girl was throwing on the seesaw, which was on a merry-go-round, something like that, okay? So then you also have this cross product of the angular velocity with the position vector between that point, because now no longer that point is coinciding with P. At that instant it was coinciding with P, but then P is moving away from that, so that position vector comes into picture now, right? Now acceleration obviously is going to be a little more complex. We'll take the time derivative of this to go to this. You're going to use the 2-point formula also in that. Once you do that, you end up with this much more complex equation, but it's essentially applying those time derivatives in an appropriate way and taking into account these two formula in terms, and when you do that, you end up with this. So once again, you see this particular term is the Coriolis acceleration. So 2 times angular velocity times your translational velocity is a Coriolis kind of acceleration, whereas in the 2-point fixed formula, we got the centripetal acceleration. In the 1-point moving formula, you're getting the Coriolis acceleration, because that's the nature of these two. This is essentially along the radial direction, remember, this is essentially along the tangential direction. And you see that this is associated with a particle which is moving, and therefore that velocity has to be there. That is not there in that because both the points were fixed, and therefore you didn't have that over there. Similarly, you don't have the centripetal acceleration in this, but you have this, sorry, you do have this particular term. The centripetal acceleration is there. You also have the Coriolis acceleration because this was derived using that formula as well. So it's using that within that, and therefore you end up with that in the first part of the equation. Okay. Next, we look at the system of particles, the causation of the motion. So therefore, there's a force which is causing that, and also we applied the Newton's second law to each particle to start with, and then summed it over. So we took the cross product of the position vector with the force, and then similarly, so the second part, of course, the force is equal to time rate of change of the translational momentum in the inertial frame. And when we did that, we substituted the translational momentum with the mass times the velocity. Then we assumed that the particle mass is not varying in time, only the velocities are varying in time, so m can be taken out. And we also started off with a fictitious quantity. Instead of r cross d by dt of this, we said, what if we start with d by dt of this cross that? We can write it as two terms, u dv plus v du. When we did that, we saw that the second term involved a d by dt of ri, which is velocity. So velocity cross velocity will go to 0 because they are parallel to each other. Cross product goes to 0. So that goes to 0, which means that this is what I have there. Now I can replace that by this, which is useful because this can be given a different context to that, which is how we went about that, and that's how we introduced the concept of the angular momentum, very similar to the translational momentum, but now a 1:1 correspondence with torques instead of forces. So, and this equation, of course, is valid only in certain cases, about the center of mass, about inertially fixed points. For general cases, it's not valid, as we already saw, right? So the angular momentum, just like torque is defined as moment of force, here angular momentum is defined as translational momentum. Now, above equation, that is this particular equation, as I said, is valid only for angular momentum, and moment about, that is both m as well as h, have to be only about certain points, namely either inertially fixed points, which we refer to as O in general, and then about the center of mass, which we refer to as C, right? The rigid body's rotational motion equation is quite simple in the form of very similar to translational momentum time rate equal to force summation. Here you have angular momentum time rate is equal to the torque summation, but you should know the restrictions in terms of its validity when this is valid, whereas that is much more generally valid, okay? So here there are many more restrictions compared to that. Rigid body is rotational motion equation is quite simple, and of course the key parts to it in terms of the further extension to this, which most of which we saw today, were about the moments of inertia and the products of inertia, and the frames of reference with which these are associated, right? Next, we also looked at the Euler's second law, which is the rotational equivalent of Newton's second law for rigid bodies, and we applied it about the center of mass, about which this simple equation was valid. Of course, this is for inertially fixed points, not for the center of mass. And then these two are, of course, related to each other, h0 and hc, by the additional term, which is the cross product of the position vector of the center of mass from the point about which you're taking the angular momentum crossed with L, right? So similarly, as far as the torque is concerned, and simple form is valid for both such points, O as well as C, right? So then, yeah. So this is straightforward, that VC is parallel to itself, so therefore that term goes to 0, and your F is equal to L dot is what you had started off with, of course. And the simple equation for Euler's second law about center of mass, as I said, has the very same form as it had about the inertially fixed point. Okay, but the utility of this, of course, is that whereas that is fixed and therefore cannot have a velocity, O cannot have a velocity, but C can have a velocity, still the simple form remains. Okay, so sometimes use the center of mass, sometimes use the inertially fixed point, whichever is convenient for the problem at hand. Okay. Next, we look at continuous rigid bodies and integrations over the areas and volumes. We dealt with this in the review already a little bit. We're just extending that a little further. Now we're talking of a system of particles, which we already just reviewed. We know that the angular momentum can be found out by summing the angular momenta of individual particles, which is just the position vector crossed with the translational momentum. And then we want to extend that from a system of particles to 2D and 3D rigid bodies, where of course we will employ the constraint that the distance between 2 points remains a constant. And like in the system of particles, the interactive forces cancel each other out. Once we do all of that, we end up with an expression for Hc, which is like this, and the first term of course vanishes, and then you are left with the second term alone, right? Now, using the rigid body frame of reference, because we cannot use any other frame of reference for this simple form, and the CG definition, we went on to define the position vector, the angular velocity, as well as the translational momentum in the same set of unit vectors I, j, k, as far as the measure numbers are concerned. And when we did that, we were able to put all of them in simple matrix equation, m equal to I omega, where I is a 3 by 3 matrix. And once we did that, we had to define, of course, all the terms of the inertia matrix, which are two kinds of terms. One set where the index repeats, called the moments of inertia, involving the sums of squares of the coordinates. The other, the products of inertia, which involve just the, as the name suggests, the products of the coordinate measures in order to get there. And important thing to remember is the negative sign based on the way we have populated these equations, how we have derived, and so for the products of inertia, always negative. Okay. In other words, this may or may not have a negative value, but there's a negative in the definition when you're taking in the product x, y, dr. Okay. Next, we talk about the kinetics for the 3D rotation. So with this, probably I'll conclude. So the Euler's second law of motion we had, which we looked at in various forms. One was in terms of the angular momentum, which is straightforward, especially for center of mass and inertially fixed point. But then we converted it to in terms of angular velocities, which is where we introduced the matrix I, and in terms of the measured numbers of the rigid body frame of reference in terms of B1, B2, B3. And then remember in the morning itself, today morning, we took a special case of B1, B2, B3, this is the principal moments of inertia, or principal directions rather, to get to the principal moments of inertia. And so equations simplify further when you're using such a principal axis system. And then the second term, which is quadratic, remember, it's a nonlinear term. It's 0 for rotations about a single axis, as well as for spherical rigid bodies, because of the geometry that is involved over there. Because remember, we were talking of the differences of IXX minus IYY, IYY minus IZZ, IZZ minus IXX. All of them will go to 0. Another example, of course, is the cube. So both those cases, if of course the vectors are unit vectors are along the parallel to the sides or edges of the cube. For rotation about a fixed axis, say a z-axis, then the fixed axis need not pass through the center of mass, but the advantage of using the center of mass, of course, is that we can allow it to move, and then we can combine Euler's second law, which is valid for rotation, with Euler's first law, and many a times these will be coupled with each other, and you'll have to solve all of these simultaneously. And some very beautiful applications of these you will see when you go on to learn aircraft dynamics, because these concepts, once you are kind of quite strong in, applying it to a problem as complex as the aircraft dynamics becomes child's play, because especially if you remember that sequence 3 to 1, for example, some of the problems that you saw today in terms of given certain roll, yaw and pitch properties and getting to their angular rates or vice versa, if you didn't have all those equations in hand, would have been so more complicated. So the fact that we were being able to derive those equations is what made those quite straightforward implementation of a formula. Okay. Thank you very much. If there are any questions, I'll be happy to answer, as always.